Hi everyone. In this video lecture, we will learn about the physiological mechanisms responsible for exciting tissues. When I say excitable tissues, meaning all tissues that are capable of propagating electrical signals. We all know that the nerves, for example, muscles, and also, well, skeletal muscles, both skeletal and cardiac muscles, those types of cells, they are capable of transmitting electrical signals. So, first of all, to introduce this subject, this is necessary to learn and understand because all this information regarding the physiology is important in order to further adjust parameters when we are dealing with electrotherapy devices. So, to introduce this topic, an electrical current is a flow of charged particles. So every time we use current, we mean that we are exchanging particles within the cell, right? So these particles, they are called ions, as well in biological tissues. So taking this nerve cell as an example, uh, a dendritic spike, for example, when an electrical charge is generated in a nerve cell, this stimulus is propagated along the nerve cells, right? In this case, we called neurolemma, which is the cell membrane of a nerve cell. Okay, so we have the electrical stimulus, and this signal is transmitted along the cell. Why does this happen? Because the cell has um, some channels, for example, ionic channels, that can change their state. They can open, they can close, therefore leading to more or less movement of particles, of ions. So the electrical currents, they act stimulating the action potential in nerves. Okay, so those currents, they cause nerve depolarization, they can cause also muscle depolarization, and also have other ionic effects. Meaning that, for example, a cell can, they can increase the cell permeability to certain types of ions. Okay, so this is also considered ionic effects when we change the permeability of the cells. The basic concepts that we should understand, physiologically speaking, is the membrane potential that we have in the cells. Okay, so an electrical potential difference exists across all cell membranes, no matter what type of tissue we are talking about. So cells, they are individualized compartments, okay, and they are separated by the external environment uh, because they have a membrane. Okay, so this membrane divides what is the internal environment and what is the external environment. And considering this membrane, the cellular membrane, uh, they have like this difference in electrical charges inside and outside, in a way that when we have an equilibrium, okay, of these charges, outside charges and inside charges, this equilibrium is called resting membrane potential. The resting membrane potential varies approximately from -70 to -90 millivolts, depending on the type of cell. So for example, a nerve, the resting membrane potential in a nerve is minus 70 millivolts. The resting membrane potential in a muscle is minus 90 millivolts. The resting membrane potential in a cardiac muscle is minus 85 millivolts. Okay, so this membrane potential at rest can vary according to the cell type. Basically, this rest membrane potential depends on the ionic distribution across the membrane and also depends on the membrane permeability. So this means that we are talking about a difference that depends both in the electric charges, the ionic distribution, and in the membrane permeability, meaning the concentration. So it depends both on the electrical charges and also the concentration. So this is an electro, the the different types, sorry, the electrical, the electrical, wow, I forgot the word. The electrical differences, gradient, this is the word, gradient, okay? So it depends both on the electrical gradient and also on the concentration gradient. So there we go. Here we have this example of a cell, and we have inside mainly negative charges, okay, or ions, proteinates are they have negative charges, and outside the cell we have mostly sodium, okay, and inside mostly potassium. So in order to reach this resting membrane potential, we must have an equilibrium in both electrical charges and also concentration of these ions. And then we have the action potential, okay? So when an impulse is generated, as you see here in this animation, normally the cell is negative inside and positive outside. So when an impulse is generated, inside becomes positive. So this causes a depolarization in the nerve. You see here, inside is positive. So the nerve is depolarizing. And the nerve impulses, they are transmitted as action potentials. So this is the typical picture of an action potential. Considering a nerve cell that we talked before, this rest membrane potential in a nerve cell is minus 70 millivolts. So we have a sudden increase here in this curve, and then a decrease, which is the repolarization. And then we have also, in the end of the curve, the hyperpolarization. But what is interesting to understand is that considering this picture, an action potential to occur depends on the electrical stimulus that will excite the cell, the nerve cell, okay? And this stimulus must overcome the threshold level. So as you see here at the bottom, we have minus 70, which is the resting membrane potential of a nerve. And then superiorly here, we have the threshold level, which is approximately minus 55 millivolts. So an actual potential to occur, the electrical stimulus must overcome this threshold level. So initially, the membrane is slightly depolarized, okay, in the resting membrane potential. So this is initially depolarized till it reaches the threshold level, okay? And then we have, next, then we have a sudden change in polarization that causes a sharp stroke. So this bit is called depolarization, which goes beyond the zero level up to plus 35 millivolts. Okay, so this is the peak of an action potential. Then a sudden decrease in polarization causes a sharp downstroke, okay, to this curve. So this is the depolarization. When reaching the resting membrane potential level here, it slows down. Okay, so it doesn't go so sharp, so rapid. It goes slower here. And if it goes beyond the resting level, okay, again, it's called hyperpolarization because the stimulus is higher than the resting membrane potential level here. So the cell can be hyperpolarized in the end. So an action potential has like um, an average duration of 1 millisecond. Okay, so this is super fast. So in 1 millisecond, we have all phases of an action potential. In 1 millisecond, we have depolarization, repolarization, okay, and also hyperpolarization in 1 millisecond. The action potentials, they act according to the all or none law. So this law means that the action potentials, they are all or none signals, meaning that they don't depend on the strength of the stimulus. Well, as long as the stimulus overcomes the threshold level, the action potential will be generated, will be triggered. So they either occur fully or they don't occur at all. Okay, so if their electrical stimulus doesn't overcome the threshold level, there is no action potential. Okay, so they will only be triggered if they exceed the threshold. Okay, so once the threshold level is reached, the action potential is set off and no one can stop it. It's like a gun. So the action potential is triggered. And what happens during all the phases of the action potentials? So the action potential starts here in yellow, when you see here this yellow part. So in this yellow part of the action potential, we have sodium channels that they open. If you see here in this picture, it also represents the same curve, okay? So we have here an example of the sodium channel opens. So the positive electrical charges, which are dominant outside the cell, they enter the cell. And this makes the internal environment more positive, as you see here. Okay, so in the green area, so more sodium channels they open and more positive electrical charges enter the cell. When we have when we have the peak of the action potential, okay, so the sodium channels they close. When the sodium channels they close, immediately, so here we have a change in polarization, okay, between the internal and the external environment. So in order to compensate these electrical gradients, okay, so the potassium channels, they open. As you see here, this is a potassium channel, it opens. So more negative charges, they So potassium ions, they exit the cell, okay, in order to make, like, to restore the equilibrium in the nerve cells, okay. So as you see here, potassium channels open, and here at the end of the curve, here in the blue area, the potassium channels, they close. So at this level, when the potassium channels close, we reach again the rest membrane potential, okay, the equilibrium at -70, okay, approximately here. And this is what is illustrated in this picture. And we have also some other concepts, okay, that this one here, we see the absolute refractory period, okay. So this period here, it means that during this period, the membrane cannot be excited again, okay, because there is an inactivation of the sodium channels, okay. So in this inactivation, so basically the channels, they have three states, okay. Those channels, they can be open, closed, or inactive. So when this state is inactive, okay, during the refractory period, it means that it is technically open, but here we see that there is a blockage, okay, by a protein. For example, a protein comes and blocks the channel in a way that no passage of ions is permitted during the inactivate state. And then we have also the relative refractory period, okay, which is this part of the action potential curve. So during this period, the nerve membrane can be excited only by supra-threshold stimuli, okay? So at the end of the repolarization phase, the inactivation gate that was inactive, it opens, okay? And then the activation gate closes, and this can be open every time we have a stimulus that exceed the threshold, okay, of this membrane. So this is the refractory period. And the action potential propagates through along the nerve cells, okay, through the nodes of Ranvier. So as you see here in each, so this is the myelin sheath, okay, and we have nodes of Ranvier concentrated. We have sodium channels concentrated in the nodes of Ranvier. So the myelin sheath is mainly composed by fat. Okay, so fat, as we all know, is isolation, is an isolator. Okay, so this is comparable to an extension cable that we all have at home. Okay, that we use to connect electricity to other to electrical devices. So a cable, an electric cable, is a metal inside, okay, and outside it's plastic, okay, or rubber. So plastic or rubber they act as an isolator, okay. So the same happens here in the myelin sheath, okay, in the nerve, in the myelinated fibers. So the myelin acts as an isolator. So that the electrical stimulus, the nerve impulses, they jump from one node to the next node. So this is called saltatory transmission of impulses. Okay, so in a way that depolarization mainly occurs at the nodes, and it goes faster because they go like jumping from one node to the next node. Okay, so this is the basics of of electrophysiology. Okay, that is nice to understand because then we'll be able to comprehend better the interactions of uh, electrical stimulation that we frequently use in physiotherapy, like TENS, for example, for pain modulation. Okay, so we will understand better how this external electrical stimulation interacts with the nerve cells, for example. Okay, so both to modulate pain and also to some electrical currents, they can be used to strengthen muscles as well. So we'll learn in the next video.